In this lecture, we're going to look at the generalized finite element method for fracture mechanics. So what you see here on your right is a representation of a finite element mesh composed of quadrangular elements, and in red you have a crack. So you see that the crack is basically subdividing your domain into let's say W alpha plus, W alpha minus. So let's say a positive region, whatever lies on one side of the crack, and a negative region, whatever lies on the negative side of the crack. Now, if you remember, we discussed about clouds, right? So for that particular node alpha, I have also said here, so W alpha plus is that part of the cloud that lies on the positive region of the crack. And you can see that the crack in red has the crack tip, right? And I have shown also here in green what would be the representative elements. So in GFEM, all the nodes that you have here should have an enrichment to be able to reproduce the right kinematics for this problem. So if you introduce a crack in that location, that basically translates into there's going to be a displacement jump along that discontinuity, and this is a strong discontinuity as opposed to what we have been doing before. In the previous lectures, we were dealing with the weak discontinuities where the jump was in the gradient. Here we're actually dealing with the jump in the field itself, and that's why it's called a strong discontinuity. So if I want to write the approximation for that problem, remember that we wrote this in different ways, but you could think of basically adding the behavior of different clouds, right? So keep in mind that all this course is revolving around this idea that you have some sort of behavior in clouds that is obtained by using enrichment functions, and we're pasting together by means of the partition of unity shake functions all those behaviors. So I'm going to write the approximation again as we have done it already. So now we are in 2D. So we're going to deal with the vector fields. So I have a sum over alpha equals 1 to n. These phi alpha are my shake functions of my partition of unity shake functions. And then I have some function u alpha in that corresponding cloud, HP. Right, so in this way, this is approximation means that we are pasting together all those different behaviors that we have in the clouds. So maybe I should move this a bit. So what this is, this will be the local approximation defined on cloud W alpha. And of course, the other way to write this by means of enrichment functions, we have seen this already, is by having a sum over the enriched space. So this u alpha I corresponds to the enriched degree of freedom, and now I have my alpha I that is a function of location, and these are my enrichment function. And this is the enrichment function. And DL, of course, is the dimension of that enriched space. Yeah. So if I want to reproduce the kinematics, the right kinematics due to a crack, keep in mind that the right kinematics means I want to reproduce a jump in the displacement field. So then I have to add a function to this formulation, this L alpha I, to reproduce this jump. So what kind of function you know can reproduce a jump? The Heaviside function. Yeah? So that will allow me to reproduce the jump in the displacement. Now, something very interesting is that if I actually enrich, let's say, all the nodes of this element here with a Heaviside enrichment, do you think I will be able to reproduce that kinematics of having a jump in the displacement? Again, yes or no? So if I add that Heaviside enrichment function to that element, so I'm basically enriching every node in that element that is crossed by the crack with a Heaviside enrichment, will I be able to reproduce that jump? Yes. But what happens here? If I take a look at this element, what do you think would happen if I enrich every node of that element with the Heaviside enrichment? Will I be able to reproduce the kinematics, the right kinematics? No. Why not? So intuitively, what would happen if I enrich every node with a Heaviside enrichment there? The whole thing is going to split, right? And that is indeed what happens. So that means basically that I'm extending artificially the crack till the end of the element, right? So in a way, if I add an enrichment function and the Galerkin framework is assigning a non-zero enriched degree of freedom that is associated to that enrichment function, this basically translates into that strong discontinuity splitting completely the element. Yeah. So you basically have, in this case, to solve this problem properly, you have three types of enrichments that you need to add. We have to deal with the smooth part of the approximation. Remember that we did the same thing when we were looking at the weak discontinuities. So there is a smooth part and a non-smooth part. So we still have to deal with the smooth part. Then there is a discontinuous but not singular. And then finally, there is a discontinuous on part of the cloud and possibly singular. So one of the interesting characteristics of this problem is that there is a singularity at the crack tip. So linear elastic fracture mechanics tells you that as you approach the crack tip, your stress goes to infinite. Okay. Of course, that doesn't happen in reality because normally we do not have a sharp crack tip, right? You don't have a crack that is so sharp that it has a zero length error, and besides, our materials have a finite strength. So that is never the case. But the theory predicts that there is a singularity at that location. So if you want to capture that singularity, then you have to add an enrichment function that behaves in that way. So what better choice than just take those functions that are given you by the linear elastic fracture mechanics theory to reproduce that. So again, when you're adding something to the approximation, if it is useful, Galerkin is going to tell you. Otherwise, it's going to be assigned a 0 degree of freedom, and then it's not going to be used. Okay. So let's take a look at these different types of enrichment. So for the first one, this doesn't change from what we have seen before. So we have the continuous part, and I'm gonna call it with a tilde to denote that it's actually continuous. And we have seen before when we were looking at material interfaces that the best functions that we can choose for this are polynomials of higher order. Yeah, so my enriched space for the continuous part where the dimension of this space is dl tilde, then you know what those are. We have seen them already in the previous case. Okay, this doesn't change.
One question.
And these, of course, give me a second.
Okay.
And these are the polynomials of degree p minus 1. And why is that? Why p minus 1 and not p? Huh? Who can tell me? Who can tell me that? Well, my partition of unit is linear, so I just need to enrich with polynomials up to order p minus 1, because when you multiply those enrichments of p minus 1 by the linear partition of unity, then you get a final polynomial of order p. Okay? So these one have or are of degree p. So I'm going to shift all of this. Okay, so that doesn't change from what we have seen already. Now for the second part, which is a discontinuous but not singular, we already discussed, and we're going to use a Heaviside enrichment function. Okay, so some notation here. What I'm saying here is that I'm going to identify those clouds with this index set ICF, which is basically the set of clouds that intersect the crack, but not the one that contains the crack tip, because as we discussed, if you're actually adding a Heaviside enrichment, right, to that element that contains the crack tip, then you are artificially extending the crack till the end of the element. Okay? So now I'm going to represent U. I'm gonna do it like this. Sometimes I like to draw symbols that represent the actual kinematics that I want. It's gonna be smooth part plus something that contains the jump. Yeah, so for the smooth part we don't do, I mean, there is nothing different from what we just discussed. And now we're going to use this Heaviside enrichment function multiplied by those smooth functions. So you see that right now, basically, I have the Heaviside enrichment function that is multiplying my continuous function. This basically means that if I have a continuous function that is obtained by several polynomials, right, constant or sorry, linear and then quadratic and so on, then you have to add also the Heaviside enrichment function multiplied by all those different polynomial orders to get basically the same degree of interpolation at the end. Okay, this is what this equation is saying. So this one, this part here is a continuous part, and this is the discontinuous. So the Heaviside enrichment function that you normally find in the literature when looking at enriched finite element methods is basically one of two kinds. The function is equal to 1 on one side of the crack and is equal to 0 or minus 1 on the other side. So these are the two functions that are usually used. So here I say W alpha positive, 0 otherwise. Or, let's just copy this. Okay. And well, for the smooth part, again, this doesn't change. It's the same as before. And now I want to use the same thing to show you the other part of the enrichment. Okay, so we're going to have and this one here is going to be h, the Heaviside enrichment, and then h times this function, and then h times that other function, and so on. And this is the way you're going to build your enrichment functions. So we actually wrote a paper where we are actually showing that when you're dealing with discontinuities and you want higher order interpolations, you have to multiply the smooth part of your interpolation with the discontinuous part to get high order discontinuous functions. Otherwise, you do not recover optimal convergence. Okay, that's the way. That's the reason I'm writing the enrichment in this form. And then finally, for point 3, which is basically discontinuous in a portion of your cloud and then possibly singular, we need functions that represent that singularity. Yeah, so say you have a crack that looks like this. Well, this is a crack tip. You can actually derive from linear elastic fracture mechanics. There are functions that usually are given in terms of polar coordinates r theta, that introduce that singularity. This was one of the groundbreaking ideas behind XFEM in the first paper in 1989 by Nicolas Mose and the people at Northwestern University. They provided basically these functions to keep or to represent or reproduce that singularity. Okay. So I'm gonna call this like that. And again, I'm going to do the same. So I'm gonna take the smooth part and I'm going to add something that can reproduce that singularity. Okay. So this is the continuous, and this is the discontinuous. Singular. And well, the functions that were given by Nicolas Mose, I have here, basically these are the people behind what eventually was called the extended finite element method. The enrichment functions that they used for that original paper are square root of r sine theta over 2, square root of r cosine theta over 2, square root of r sine theta over 2 sine theta, and the square root of r cosine theta over 2 sine theta. So let me just move this. But these are not the ones that are actually derived from linear elastic fractal mechanics. So Nicolas Mose proposed this set of functions. Actually, if you take the derivative of these functions, they all exhibit this 1 over the square root of r singularity. So as r goes to 0, then you are approaching the crack tip, and then your gradient blows up. So that is the singularity I'm describing, right? But these are not really the functions that were derived from linear elastic fractal mechanics. But those have actually been used, and in fact, they behave better than these functions, and this is shown by Carlos Armando Duarte in some of his papers. John?
Yeah, are you sure you wrote the third component right? Because the third term is sine, but the fourth term is cosine, sine.
Yeah, so I'll check on this. You're probably right. Yeah. I have to check on this. Yeah, I'll check on that and then I'll correct it. Okay. Yes, you're probably right. It's probably, yeah, exactly. It's probably cosine theta in the end. But I'll double check, right, just to make sure. So that I'm going to write for completeness. So these are not the functions that are actually obtained from linear elastic fractal mechanics from the theory, right? But you can actually use those.
Sir, can you explain what the angle theta? What is that about?
Yeah, it's just the polar coordinates. If you have your crack, you have it here, right? You can set a local coordinate system, polar coordinate system, in the direction of the crack. So these are just polar coordinates, right? So as your radius goes to 0, your stress becomes singular. Okay? So theta is basically the angle between that direction of the crack and your r vector. Okay? And this actually has been done by Duarte.
But what determines the angle between those two vectors then? So between the r vector and the vector that is along the correct direction.
Yeah, so this is just a function. It's just represented in polar coordinates. It's just that it's given in terms of theta because, well, you know, a crack can have any direction. So the idea is that you are always at the crack tip, and your theta is measured from the direction of the crack. That is the idea.
Yeah, but you said the angle is between the vector r and the vector that is along the length of the direction of the crack, right?
Right. So this here, if I can say, this vector that I draw is E1, for example. Yeah. Theta is the radius, like the angle between that vector and r. Okay. That's theta.
Okay.
Okay. Because all these solutions are, you know, these are analytical solutions that are obtained, for example, using some particular methods, and they place the crack in an infinite space. So you are looking really at what's happening at the crack tip. And since this can be in any direction, so the convention used in linear elastic fracture mechanics is that your functions are given in polar coordinates from a system that is placed at the crack tip. All right? Okay. Now there is a little thing here that I want to discuss just to finish this. You can think of enriching the elements that contain the crack tip with those singular functions, but there is a problem here. What happens when you are basically making mesh refinement, and then you're thinking, well, I'm going to make my solution more accurate, and I'm going to make my mesh smaller and smaller and smaller. What is happening? Who can tell me? So in other words, the element that contains the crack tip is going to be increasingly smaller and smaller and smaller.
The crack tip may correspond to an element.
Yeah, but let's take a look at that element that always is going to contain the crack tip. What is happening if I make it smaller and smaller and smaller, and I keep enriching only the nodes of that element? What is your intuition? What is happening?
R becomes smaller and smaller.
No, R is a defined, you know, it could be any point around the crack tip.
The crack tip is coming closer to your nodes that you enrich?
No. No ideas? What effectively is happening is that you're enriching an increasingly smaller area of your domain. Okay? And this is not really reproducing the physics of the problem, because you would expect, well, if I have a singularity, that this singularity is irrespective of my mesh. So there is then a coupling between the discretization that you're using and your enrichment strategy. You see what I mean?
No.
So what I mean is, if I enrich right now this mesh that I show here with singular enrichments, right? Those singular enrichments are going to be valid in every cloud of every node where I place those singular enrichments. Okay? Now, as I refine my mesh, those elements that have the singular enrichments are going to be smaller and smaller and smaller and smaller, which effectively means that I'm enriching a smaller portion of my domain. And therefore, this is not really representing the physics of a problem, because you would expect that the singularity that is produced by the crack has nothing to do with your mesh size. You understand? And so there are two different strategies to place these enrichments. You can say, well, I want to just enrich the nodes of the element that contains the crack tip with these singular enrichments, but then you have this problem. A different approach is, okay, I want to enrich an area around the crack tip, right? And I make this area, let's say, a circle of radius r, and I make this area constant regardless of the size of your finite elements. So for some discretization, you may have some elements that are enriched with these functions, right? But when you are refining the mesh, then you are enriching more elements, and this makes more sense. So this is basically the difference between what they call topological or geometrical enrichment. Right? So when you're talking about topological enrichment, your enrichment is increasingly vanishing as you are refining your mesh size, whereas if you're using geometrical enrichment, you're basically placing enrichment in a region regardless of your discretization. And this makes more sense. Okay? So let's write that down to finish this discussion on XFEM. This is all we're going to look at in XFEM. So there are two little things that we need to be aware of. One is, as the mesh size h goes to 0, the area this is one. And then the other thing that we have to be aware of is that these particular functions have issues in blending elements. So now the error, you're going to have error in some elements that are blending the standard finite element part from the enriched part. So let's write this down and let's finish. And then there was a proposed decorrected XFEM. Is a method that was proposed by Fries. I talked already about this in 2007, that is supposed to address this issue in blending elements. All right, so we're done with XFEM. The next lecture, we're going to look at the discontinuity-enriched finite element method. Okay?